went ahead and wrote down part H, starting the next section of integrals. And again, trigonometric substitution. This time I have a number minus x squared. That means I'm going to use sine. When we had the plus sign, we used tangent. If we have x squared minus a number, then we use secant. So this is a job for sine. X is equal to 3 sine theta. Dx is 3 cosine theta d theta. So now the substituting part. Instead of dx on top, I have 3 cosine theta d theta. Instead of x squared, I have 9 sine squared x. And then under the radical, I have 9 minus 9 sine squared theta d theta. And yes, that should be a theta, not an x. So I have 3 sitting on top and 9 sitting down below. So I'll rewrite this as cosine theta d theta, and I'll put a 1/3 out front. I still have sine squared theta down below. This is the same thing as 9 times 1 minus sine squared, which is the same as 9 times cosine squared. So when we take the square root of it, we have 3 cosine theta. Cosine cancels with cosine. I'll bring this 3 and combine it with that 3 and make it a 9th. I have d theta sitting on top, and I have sine squared theta on the bottom. 1 over sine squared is cosecant squared of theta, and the integral of cosecant squared is negative cotangent of theta plus a constant. Draw my triangle. Theta is right here. Sine is equal to x over 3. That means opposite over hypotenuse. Adjacent is equal to 9 minus x squared. So cotangent is equal to adjacent over opposite. Plus C. Next problem. Oh, that one looks a little different. That looks like something we would use the product rule on, and when you think about the product rule, you think about integration by parts. This is x squared times natural log of x. Now, how do we choose? I always want u to be something that's easy to take the derivative of, and dv to be something that's easy to take the integral of. Log is definitely not something easy to take the integral of, so u is equal to ln. If you have a natural log, it's going to be your u. So du is equal to 1 over x. And then dv is equal to x squared, so v is equal to, add 1 to the exponent, divide by the new exponent. U times v minus the integral of v du. So 1/3 x cubed over x dx. write it down here a little neater. I have x cubed times the natural log of x over 3 minus 1/3. I have x cubed up top with an x down below, leaves me with just x squared dx. And I have 1/3 times x cubed over 3 plus a constant. And yeah, you could do some multiplying, make it look a little friendlier. Okay, I'm going to take a break and write down part J. Now, I knew exactly what was coming when I looked at part J, because I saw 1 plus a variable with an even exponent on it in the denominator. And that made me think about arctan. And I looked up top and I realized that if I let u be equal to x cubed, then du would be 3x squared dx. I have x squared sitting up top, so magical things would happen. So this one's very straightforward. We have the integral of x squared, 1 plus u squared du over 3x squared. Those go away. So we have the arctan or inverse tangent of u, and u happens to be equal to x cubed plus a constant, and don't lose that 1/3 sitting out front. Okay. Easy enough. K looks suspiciously like a loopy integration by parts problem. E to the 2x sine of 3x. Now, how do I know that? Because I have e to the something, and I have a trig function. And generally, when you have those two things in the same integral, you have a loopy integration by parts problem. So let's start with u equals e to the 2x. Then du is equal to 2e to the 2x. And dv equals sine of 3x. So v is negative cosine 3x over 3. I'm going to take a minute and substitute all that in and see what the heck is blowing up my Teams over here. Okay, I plugged in u times v minus the integral of v du. I combined the minus and made it plus and brought a 2/3 out front. And now I have something else that jumps up and down and says integration by parts, please. That's your only hope. So for this piece, I'll again let u be equal to e to the 2x. So du is 2e to the 2x. dv is going to be the cosine of 3x. So v is going to be sine of 3x over 3. So now I'm going to plug all that in and do some simplifying, and we'll meet back here. You do the same thing. So I plugged in u times v minus the integral of v du. I replaced this that was inside those big brackets. So I have 2/3, and actually I forgot to distribute that 2/3. So I really have 2 times 2 on top, which is 4, 3 times 3 down below, which is 9. So that's my way of reminding you, don't forget to distribute your number sitting outside of those parentheses. Now remember, we have our starting equation, which was the integral of e to the 2x sine of 3x, sitting over here on the left-hand side, even though it's way up here. right there. This is all equal to that. So if I add 4 over 9 times that integral to each side, I have 13 over 9 times the integral e to the 2x sine of 3x on the left-hand side is equal to negative e to the 2x cosine 3x over 3 plus 2e to the 2x sine of 3x over 9 plus a constant, because I got to get that plus a constant in there somewhere. So now I just multiplied both sides by 9 over 13. And e to the 2x sine of 3x dx is equal to 9 over 13 multiplied here gives me negative, let's see, 9 cancels with the 3, leaves me with 3e to the 2x cosine of 3x over 13, and the 9's cancel, 2e to the 2x sine of 3x over 13 plus a constant. Be very careful with all those fractions. That's where you're most likely to mess up on one of those. Give L a try on your own. We'll meet back here and compare answers. If you have the formula for the integral of natural log memorized, good for you. I don't happen to have it memorized, so I'm going to have to use integration by parts to do it. Now, just for fun, I decided to do this different than it is on the key. I have the key over here to make sure I don't make big mistakes. So first thing we did was our integration by parts, and then we ended up with the integral of 2x over 2x plus 3. On the key over here, I did some long division, which certainly works. You divide the bottom into the top, and you end up with a simple integral. Over here, I did it with a double substitution. I let u be equal to 2x plus 3, so then 2x was equal to subtract 3 from each side. So I ended up with the integral of u minus 3 over u. Same thing down here, divided it into pieces. And I have the exact same answer, even though it looks a little bit different. If you look at the key, I'll pull it over here so you can see. Here's where I did the long division on the key, and I did 1 over 3, 1 minus 3 over 2x plus 3. I have minus x, so here I have minus 2x over 2, which is minus x. I have 3 halves of the natural log of 2x plus 3. I have this extra minus 3 halves when I did it this way, but it doesn't matter because I have the plus c, and that c can be anything. So those are the same answers, two perfectly valid ways of doing the same problem. Always fun when you can do it two ways. Okay, almost there. Let's look at M. M looks like one of those integration by parts that you can do with a table, because x squared is going to get more and more simpler every time, more and more simple every time we take the derivative. More simpler. So we have integral of x squared cosine x. Now, of course, you could just do integration by parts twice. It wouldn't be that bad. But if you had x to the 5th power there, you might not want to do it that many times. So I'm going to make a u and a dv. U is the thing that gets simpler every time you take the derivative. X squared, 2x, 2, you keep differentiating until you get a constant. dv, we start with cosine x. Integral of that is sine. Integral of that is negative cosine. Integral of that is negative sine. Plus, minus, plus. That one goes with that one. That one goes with that one. That one goes with that one. So, x squared, sine of x, I have minus minus, so plus 2x, cosine of x, minus 2 sine of x, plus c. Again, if you would prefer to do it by doing integration by parts twice, same answer. Life is good. N looks kind of tricky. We have integral of sine of x times cosine of x over 2. So we have two different inputs on our trig functions here. So I'm going to think about the trig identities that I know. I know that sine of 2x equals to cosine x sine x. So let's see if that would help me. Yes, I think it would, because I can rewrite sine of x as 2 cosine x over 2 sine of x over 2. Because here is my original rule, sine of 2x, so sine of plain old x, and let's make it more clear, sine of 2 theta is equal to 2 cosine theta sine theta. That's the identity. And I replace 2 theta with x, so theta is x over 2, x over 2. So now I have everything written with x over 2's. This is 2. I'm going to write sine first. And then I'll put the cosines together. Cosine of x over 2 times cosine of x over 2 is cosine squared. So I want u to be equal to cosine of x over 2. du would be equal to 1/2 of sine of x over 2 negative 1/2 of sine of x over 2 by negative 1/2. So we have negative 2 sine of x over 2. So 2 sine x over 2, u squared, replace dx with negative 2 du over sine of x over 2. Cancel. So negative 4 times, add 1 to the exponent, divide by the new exponent, and don't forget to add c. I brought u back at the same time. O looks like a very simple partial fraction decomposition. So I'll do that. We'll meet back here and compare answers. Oh yeah, that's the problem that you hope to get on test day. Nice and easy. Everything's easy to plug in. So negative 1/5 natural log of x plus 4, 1/5 natural log of x minus 1. Okay, I'll come back and we'll do problem 2 and maybe 3 on the next video.